Also, Patricia, you want to an introduction?
So yeah, I guess a lot of us already know Xindi because we've talked about so many of her papers on Slack. She's surprisingly only a third-year student in PhD, given all the relevant things she has done. A lot of data set distillation work, data selection work for VLMs, and now also in compositionality. She was at CMU before, where we met, and now she's doing a PhD at Princeton. And we're excited to learn what she's doing.
Thank you, Patricia, and everyone else for having me here. Okay, I can get started. So today I'm very excited to be here. I feel like this is the place that I don't need to convince people how important data is. But I will start. So the topic of this talk is from data to capability, data for efficient multimodal machine learning. So before we begin, a quick intro. I'm currently doing my PhD at Princeton. I'm a rising fourth year. I did my master's back in San Diego outside Robotics Institute at the by the way, can everyone on the Zoom hear me?
Yeah, sounds great.
Okay, perfect. Yes, and so my research focused on the data for efficient multimodal machine learning and developing data-centric approach that can trace model performance back to training data composition and introduce data-driven capability to optimize learning. Yes, so currently I'm interning at NVIDIA this summer. I'm also working on related stuff like trying to understand the motion from data perspective for video diffusion stuff. Yes, so although I feel like everyone here are on the same page, data is super important, but I'm just gonna give a super quick why we want to study data. So we're in this remarkable era for machine learning, and in just the past few years, there's been significant progress across areas like generative AI, robotics, and AI for science. And in all those applications, data plays a super important role. I was actually putting together those screenshots this morning. We've seen that generative AI models they are trained on large-scale data sets to produce realistic outputs across various modalities such as image, video, text, and audio. And so many companies and industries are working on, for example, video generations or large language models. Like we've seen significant progress over the past few years. And at the same time, we also see the success of robotics industry. And the robotics systems relies on training these comprehensive data sets that represent a wide range of environmental conditions. And so this will enable them to safely and effectively navigate and complete their assigned tasks in diverse situations. And also, for unlike many other domains, the scientific problems often involve complex structures and physical laws. So the quality, accuracy, and scale of data are critical for machine learning models development in AI for science. Here's a demo from AlphaFold from Google DeepMind. So my PhD work explores these three pillars: the compressibility, compositionality, and controllability. So for compressibility parts, for this pillar, I try to study how efficiently we can learn from or represent data, and how can we do more with less. And for compositionality, this thread of work, I'm trying to study how well models generalize to novel combinations of concepts. And for controllability, this part we try to study how precisely can we control the generation. And I will mainly talk about this following three work today. I will spend a bit more time to talk about the icons for the vision language data selection work, and I will probably talk about the two work on compositionality, compact, and also content mix. Probably I will spend 15 minutes to talk about that. Yes, so for the first part, compressibility, how much data do we actually need to train those powerful multimodal models? So instead of blindly scaling up, we explore how to compress large vision language data sets to smaller and more effective data subsets. So through methods such as data set distillation and influence-based, like gradient-based vision language data selection, we show that models can match or even exceed full dataset performance use only a very small fraction of the data. So this work sort of laid the foundation for my own understanding of data efficient learning and to identify what data matters most. And from there, a natural question arises, which is, are we keeping the right capabilities when we compress the data? And so that question led me to the whole studies on compositionality. So this thread of work, we're trying to understand the ability of models to generalize to novel combinations of familiar concepts. And we found that many vision language models perform well on atomic tasks, but struggle with complex ones that require composition. So we developed some the benchmark a benchmark concept mix and also a data recipe compact to these two works we aim to measure and effectively improve models' capabilities. And from there, we moved one step further, which is even if a model can generalize well, can we steer it towards specific outcomes? And that brought me to controllability, so the ability to precisely guide generation in multimodal models, especially for tasks like video generation. And so by introducing external memory modules and structured conditioning, we study how to maintain coherence across frames and guide generation to follow specific instructions. So this enables more persistent control in multimodal settings. All right, so that's sort of the overview. Also, another thing, feel free to interrupt me at any time and if you have any questions. All right, so for the compressibility part, I want to talk about the vision language data selection work we did recently. So this paper we call it ICONS, it stands for Influence Consensus for Vision Language Data Selection. So this work was done with joint collaboration with my co-authors Mengzhou, Rulin, Zhiwei, Pangwei, and Olga. Yes. So as we all know, the training data is a key driver of model behavior in multimodal machine learning system. And from 2014 until now, we've seen so many vision language data sets such as like Flickr 30K to like Datacom or to Cambrian 7 million data set from last year. So the scale of vision language data sets has become bigger and bigger over the time, and they reach millions, even billions number of samples, and the data is often too noisy and too complex. And here's a visualization of the data that we study in this project, which is visual instruction tuning data. And so it includes the image and also the paired up question answer pairs. For example, we also see like more complex ones, such as have this like more open-ended question answer pairs. So for this round of work, people usually evaluate on a bunch of benchmarks. For example, VQ V2, which is more like yes and no, or like or lava bench in the wild, which is more on open-ended question answer pairs, or another bench, which has more of like multi-choice question. So for all those model development, one challenge that people have always encountered is high computational cost and storage demand and long development cycles. So this research question And we identify a compact subset of training data that preserves model capability while enabling faster experimentation. So ideally, we want to identify and extract the critical information from the data set. And so in this work, we introduce icons, which is a gradient-driven influence consensus approach for data selection. And we created the lava icons 133K, which is the 20% subset of the lava 665K data set that was commonly used for visual instruction training. And Cambrian icons 1.4 million, which is also a 20% subset of the Cambrian one, Cambrian 7 million data set. So both demonstrate the strong transferability across on-send tasks and scalability to larger models.
So when you say this, does it also mean 20% of the compute? Or
Yes.
okay.
So so the overview here, our approach includes two stages. The first stage is specialist stage, which computes the classes data for the course, and second stage, this generalized stage, which aggregates cross-task influence via majority voting. So the goal is to prioritize samples that are influential across multiple tasks to optimize overall. And here's an overview of the pipelines, and we'll dive into each specific part. So given a large-scale visual instruction tuning data set, we the goal so here it includes the image and also natural language instruction and also target response. And we can say that and also we have downstream target tag. For example, here we have task P1 to PK, and each of them have validation data, which is a subset of the downstream target task. And our goal is to select a subset S, which maximizes the model performance across multiple downstream tasks. And so here we want to maximize performance, and the way we measure it is we measure the performance of the subset, the selected subset on the downstream task versus our entire data set on the target task. And we have their relative scores in Korean. So here we can so this is how we define the average relative performance across all tasks as REL here, and it quantifies the subset trained on the model's performance relative to that of the model trained on the entire data set. And here we estimate how individual training example ZI affect the validation loss by measuring their gradient alignment is reducing validation loss on validation set, which directly impacts the targeted task specific evaluation scores. And when training this SGD and the bench size of 1 using data point at time step P leads to a model update here. And to reduce the computational cost, we use the first order Taylor expansion to estimate the loss on a given validation data point at the time step P plus 1 as follows. So the gradient based selection approach, they usually select the training sample of Z that maximize the gradient inner product through a Grady first order approximation, which leads to the larger reductions in validation loss for point Z prime. So while this approach omits second order terms compared to previous works such as influence functions, it provides us an efficient approximation for ranking the impact of training samples.
So how do you select the best like small t for this? Isn't that also like critical? Like at what time do you test this gradient?
Great question. So here we use the warm up model. So basically, the model checkpoint we use, we didn't actually train on the data that we wanted to select from yet. So we only use 5% warm up. Basically, we did a bunch of evaluation study to show that 5% warm up gradient are give us good signals to use for selection.
And it's trained on a full data set.
Uh,
5%
5% of the whole data set.
of the whole data set, and then you go and think that's the value.
Right.
Do you think this will change with respect to the time? Like maybe like towards the end of the training, there are different examples that are more useful because like they are more learnable or something like that?
I mean, if we switch to a different data set, will this 5% be optimal?
No, like for instance, yeah, right now using the 5% checkpoint to find which examples are most like aligned,
Right.
But what if you are close to the end of training? Like would there be different examples that are being learned more at that time? And so
Right.
because maybe the harder examples are still to be learned and they are the only ones who contribute to the gradient and so they have difference in
Yeah.
chosen examples.
Yeah, great question. I think there is some work sort of basically if you train with multiple epochs and whether the data that we've seen before it is really meaningful to learn to say the same data point again. And so I think that that sort of I think this round of work sort of explain that like what kind of data would be more impactful. Like let's say at the end of the training, the first epoch, and if we use that checkpoint to further select data, I think in our setting or like the vision instruction tuning setting, people usually go with one epoch. So you only train on the entire data set once. And our goal is to basically select this 20% of the set that would impact the most for the model training. So we actually also tried with like the final checkpoint. It actually doesn't have like
That one.
that good of a performance
Yeah.
compared to 5%.
I had a question about like what, how, or I guess what gradient you're using to get this similarity, because I think some gradient-based methods, like because the gradient for these models is so high dimensional, the cosine similarity is just like not very informative because in high dimensional spaces, like everything is very spread out.
Right. So in our case, we so here I showed some more details here. So basically, we use the warm-up checkpoints, but we also projected. We use a random projection to make sure that the gradient is not like huge to compute. So yeah, like we take the so we trained with the LARA version, and that is already like much smaller than the full model checkpoints. But yeah, to answer your question, we use the LARA model checkpoint, and also we projected it to like a lower dimension. And then so basically here the details here we first do the step 1 warm-up training. This is a very lightweight warm-up phase. It's just 5% of the data. And then we have this gradient computation stage, which we compute the gradients for both training and validation data and compress the gradients via random projection. And here the third stage we have this influence metric computation part. Basically this part we compute the influence scores to quantify the impact of each training data on the downstream validation set. So for the influence metric, each entry is the influence of the data, the training data I on the target validation data J.
I had another question about the gradient. So
Yes.
is there a specific token whose gradient you're looking at, or are you averaging the gradient across all tokens?
We average over tokens.
Like, so if the output is like multiple tokens, like which token gradient are you? Are you like taking the average gradient over all tokens?
We use the average one.
Average, okay.
And is it average across all the tasks?
Oh, great question. That's exactly what we did for stage 2 for the generalist stage. So basically for the generalist stage, the TLDR, few words to respond to your question, majority vote. So we tried actually a lot of different sort of aggregation approach. I will show in the equation later, but majority vote works the best.
Yeah, and that's a, so you start with an I by J matrix, where I are the number of training points, J are the number of validation tasks, in the specialist version that you had, right?
So in the specialist, basically we have, so the I here is the training data, J is for the validation.
So I is the number of training data points, and J is the number of validation tasks.
So you can think about stage 1 is, we're just looking at one task. We look at each individual task here, and so we have n training data points. For them in the lava cases, this is the 5K. And then for the validation data point, the number is different.
I see, but it's actually the number of unique data points in the validation
Exactly.
task. Okay, I see. So you can I by J matrix where I is the number of training points, J are the number of validation points.
Exactly, yes.
So do you average it across the task, then data points within a task, or you can put
Wait,
overfit on like relevant example?
We actually average over different validation data within one task.
Okay, so because then it will prevent some overfitting on one
Right,
example.
right, exactly. Yeah, we average over a bit within one task, but then across different tasks. I will talk about why we didn't do that later. Yes, so for the second stage, basically the goal is to select a subset that works well across various different tasks, and we address this connection between task-specific rankings and overall dataset optimization basis majority vote approach. So I will dive a bit into this
I'm
part.
really very curious that you have specialists before generalists, because
Oh,
these
yeah.
days everyone's talking about annealing with
Yeah.
specialist things towards the end.
Yeah,
So maybe at the end we can
yeah,
talk more about it, like how this thought process is like kind of like opposite to my natural.
Right. Yeah, I feel like it's I think people talk about generalists to specialists in the model setting a lot, but I feel like in the data setting, one difference is that let's say you have various different data sources and and this data also comes from like a sort of a continuous, right? Like it's sort of like a continuing learning. This year you have millions of data, and then next year you have new data, then how do you combine them? I think sort of going from a specialist to generalist type, yeah, I think that's sort of the philosophy that I currently have, but here's to hear everyone's answers. Yeah, so recall that our goal is to identify this training subset as star. And so there are multiple ways to tackle this, and depending on the assumptions that one makes about the task-specific influence scores. So the simplest approach is to merge together all the different task validation sets, and then compute the total influence score for a training example as follows. So a similar aggregation approach is the one that I sort of suggested in the last and a few other papers. So the influence of the data is measured as its highest influence on any task. And so the set of training samples with the highest aggregation influence scores would be selected for inclusion in the training set as merge and correspondingly as max here. So both approaches require that the influence scores should be like well calibrated across different tasks, which we will show later why this may not necessarily be the case. An alternative approach, which does not require directly comparing the influence scores across tasks, is to leverage the relative rank of the training samples within each task, and which is this round robin. And so concretely, we can compute the basically the rank for each example relative to other examples for each task according to their influence scores and select them and save them to the selected subset. And here, so for alternatively, we can select the training subset as mean rank such that all the examples within it have a low rank for some task K. And so basically, all of the examples that are not included in S would have high relative ranks for all task K. However, this approach does not consider the potential interplay between tasks. And since our goal is to maximize the sum of the relative performance across all of the tasks, thus if a training example is beneficial for multiple tasks, we may want to include it even at the expense of a lower ranked sample for a different task. So here we introduce the simple consensus-based voting strategy that sort of identify the training samples that can consistently show a high influence score across different tasks. So concretely, if we look into the sample, basically for across all of the tasks, we have we set the threshold, but the threshold is different for different tasks. And the threshold is the top, basically, the top 20% of the we assign the top 20% of the selected sample is score 1. And if it doesn't fall into the top 20%, we give a score of 0. And then we sum all of the votes for each sample, and we rank and select the top 20% of the samples as our final 20% subset. So yeah, for so basically this sort of identifies the unique subset of samples that are consistently influential across multiple tasks rather than those that might only be highly influential in like a few tasks. Yeah, and after we compute these scores, we rank them and select the top, for example, top 20%. And so the sort of this key basically one of the key leverage we have, key advantage we have is that it does not rely on calibration of scores across tasks. Does not make any assumptions about the relationships between tasks. So basically the generalized stage converts each task rank list into a binary vote. And so this approach basically avoids selecting very long tail samples that could only be super beneficial to one task, but in general it's not very beneficial for all of the rest. And for other experiments, we tried this a few different data sets, lava and Cambrian. We also tried a smaller data set as well. We tested out on different benchmarks, and we primarily used the lava 1.5 billion model for the selection purpose. So we compared a lot of different baselines. I will also go into more details later. So the performance that highlights is that we selected 20% of the subset for this different data set, and we that maintains more than 98% of the full performance. And at the 60% of the selection ratio, it even exceeds full performance. And we also show a strong generalization to FinTech for different architecture scale. So here we show this is the performance compared with different baselines, and we can see that the best and the second best results are highlighted here, and our method icons achieves the highest overall relative performance, 98.6%, and consistently outperforms existing approach, including coincides and also representation-based data selection. I will talk about later. So some highlights here. One thing that I do find is super interesting is that, so we compare our method against the representation-based data selection, a pretty strong baseline in the language-only instruction tuning setting. So the representation-based data selection RDS, we still use the same strategy. We compute the training validation similarity using the final layer representation of the instead of the gradients. And for fair comparison, we use the same influence metric formulation and apply the majority vote as well. But we show that while RDS is, as in previous papers, sort of show that RDS is pretty effective in the language-only setting, but in our vision language task that it sort of demands high alignment between different modalities, where the representation similarity is limited as it only sort of reflects the current embedding proximity. And so the gradient-based approach can directly estimate each sample's contribution to the validation loss.
So when you compute embeddings for vision and text, like joint, like it's like everything's in the token space. So then you just take like the average embedding.
Yeah.
But there's autoregressive, right?
Yeah, so
Because there's no
we-
real like bidirectional model which does image text together like that.
Right, so in this setting, we because a lot of models, for example, we tune a backbone and then you have the image vision cover at the beginning. So
Right.
so it's used pretty similar to the like it's not the contrastive, it's not clip style.
Right.
Yeah.
Because like in the text space, people talk a lot that the autoregressive embeddings are usually worse than like from bidirectional models like
Oh.
Word. So I'm wondering if that is also a reason why embedding based approaches don't do that well in VLM, because we just don't have good embedding capability of like adopt like imaging coded text and full text. Like you're taking the last token or something like that.
Right, that's right, yes.
Also, I think one of the most interesting thing for me on this table is that random is third best among
Oh,
like
random is pretty good, but also we show like later in the appendix, we sort of show that random also have like a huge range, so
Okay. It's very random.
it's pretty random. Yeah, and we reported the scoring was because the previous work coincide sort of reported 98.8%, but we show that like across different rounds, they really give us our different performance.
I also have a question, like what tasks have been used to sub-select the data points and what tasks being used to evaluate? Is there any correlation, like if we specifically tune upon this task, will we see improvements on this task?
Great question. So in this setting, we in this table, we use a target task. Basically, we use the validation data from each task. But later we show that we also actually in this slide, we show that it can generalize to unsigned tasks and have like a pretty high performance as well. So those tasks are not used for the computing influence scores and stuff. So this sort of shows that like once we use those target tasks to help us to guide us select a subset, it can already build a knowledge pool for vision language tasks that can be generalized to like different downstream tasks as well.
Do you have any experiments where you do 5 box of 20% data?
Yeah, so
Actually we didn't, but that's a great question. Yeah.
I have a related question, which is this assumes that you're trying to sort of match quality and minimize cost or minimize resource use. How do you think like this method would change, if at all? How would you change the sort of experiments if you want to maximize model quality, assuming some like similar amount of resources to the baseline? So like the simplest thing I think is the Bertufrecht suggestion, which is like just repeat the data for 5 epochs. Like I could imagine you could probably sample with probability like proportional to the score or something like that. But I'm curious, how you would do this if you want to maximize model quality.
Great question. I think my first intuition when this asked this question is that basically it depends on the data scale that you already have. Like for example, I think if you have a relatively small scale, then probably you want to optimize or like train more epochs and see whether the performance would keep in place. But I think there, like if it's more like larger scale and you just want to train on all of the data set once, so I think it really depends on how much performance gain you have from like training on multiple epochs. I think there are also a lot of work focused on data duplication. I think the motivation behind that is sort of like aside from the efficiency perspective, another thing is that training on the same data point doesn't give that big of a performance boost. So I think if we are asking for a trade-off between do we want to I do think another research question would be really interesting to ask is what are the data point that would be meaningful to train for multiple times, and what are the training points that can already be learned in this first epoch, or if we are gonna build train the data set for the second epoch, what kind of data we still want to keep in the second epoch. I think there are a bunch of work sort of done from the data hardness perspective, and I'm also curious to hear what you guys thought.
Awesome, thank you.
So for the we tested on Cambrian 7 million and vision learning as well. It also have relatively good performance. And for the transferability, the selected sample can generalize well to answering tasks, and also so the 7 billion model selected subset can also work well for the 30 billion version. So it also shows that they have generalization across different models. So later we did this whole ablation studies on different aggregation approach. So the score-based methods such as merge or max is sort of assume the influence scores are comparable across different tests, but we find that it's not true. Like the score distribution vary a lot across tests and making those methods slightly unreliable. And for rank-based approach such as round robin or min rank, this sort of avoid the calibration issues, but can overrepresent outlier tasks and hurt the overall balance. For example, in this case, they sort of focus a lot on the lava in the well, which is kind of like an outlier, or I wouldn't call it outlier task, but like it's very different from all of the rest tests because it's more like the open-ended study, and their answers are usually much longer than the other benchmarks. And so our voting-based approach does not assume score comparability. Instead, it asks how many tests agree that this sample is important. So this sort of gives us a more balanced and like stable selection.
Is the rank computation very expensive?
It doesn't. Actually, not really. No. You can compute them. Basically, you can get the rank of each sample and then just sort them. So
The validation tasks are not that thing.
yeah, I think exactly the validation points are like much smaller than training data. I think the most computational heavy part of this approach comes from training data gradient computation. Right. And then we show that we evaluate the icons against baseline models methods across different selection ratios, ranging from like 5% to 60%. And I think the very cool part is that icons can outperform baseline approach across different ratios, and they can exceed the full data training at 60%. So this sort of shows that our hypothesis is that icons can also effectively filter out actually harmful or noisy training samples that might negatively impact the model training process. And here we show like this is the pairwise overlap map, and it reviews significant variation in training data influence ranging across different tasks. So we sort of show the high overlap between different tasks, suggests that they have certain samples that would be beneficial across similar tasks. But for tasks that are very different from each other, they have low overlap across different selected samples. This shows that highly influential samples for one task may have limited impact on the others. And here we also show that the overlap between specialist and generalist selection, it varies significantly across different tasks. For example, we could rate to have the least overlap, and lava in the wild benchmark have the highest overlap.
Is it related that Lava W bench was also the task on which you were not doing like better comparing to baseline? That there is a higher percentage of generalist overlap?
Right,
So it was the
so
last one in the column, right? Where the
Yeah.
baseline was a little bit better.
yeah, so the lava in the wild benchmark, basically this I would say this one has like it's very interesting, like it's kind of different from others, but then you also see that from the generalist and specialist overlap perspective, they the generalists also like do select a lot of samples that like have higher overlap with lava in the wild, but one thing is this validation set is pretty small, like the entire benchmark have only like under 100 samples, which could also play a role in the selection.
Actually, the number of validation samples, is it correlated with the quality would also be very interesting.
Right. I think that for certain benchmark that already have validation set, we just use it
The whole
directly.
thing.
But for the ones that don't, we randomly selected them. But yeah, I would also assume if the selected ones are also like can be highly representative of the task, then we'll also further improve the performance. Yes, so to summarize, we introduced this approach, and it's a gradient-driven influence consensus approach for vision language data selection. And we achieved the selected subset, 20% subset, can achieve like over 98% of the full performance, and 60% of the selection ratio, it exceeds 103% of the full performance, and it also shows great generalization, strong transferability to the on-site task for different model size, and hopefully this can guide us through like the next generation of the vision language data set. Yes, so looking forward, I think there are a lot of interesting questions to ask here. For example, what data are most important for the capability of foundation models, and what is the optimal data recipe? And of course, like there are a lot of discussion on the model size and data set size. And can we also develop a more rigorous understanding of what increasing the scale does to the training procedure, and how does design emerging capabilities come about? Yes, so I was originally going to talk about data work, but we have 5 minutes left. But so I think I will quickly just give a super quick like TLDR of this volunteer work. So the two works that before the compositionality part, another work is on the vision language data selection, data set distillation, and I think vision language data set distillation, the difference from data selection is that it doesn't select those real samples in the training data set anymore. We sort of generate those synthetic data set using like also using the gradient based approach. Basically, we have this bi-level optimization loop, and we try to sort of save the performance in the data space instead of the model space. And the data set distillation sort of operates on like a much smaller scale, like even under 5%. But this, I would say, also suffers some like the common limitations from the gradient-based approach, which is high computational cost. And for the compositionality part, like concept mix. So the TLDR is we have this benchmark trying to evaluate the compositional image generation quality and with like controllable difficulty levels. And so we show the okay, so maybe just one sentence here. Compositional capability is one of the most challenging tasks in TPI generation. And the one takeaway to have from this evaluation work is that most of the sort of TPI models suffer from this limitation. And I want to show just one image here. Oh, okay, here. So we tested on a bunch of different models and so this work we put it out last year, but we haven't tested out on the most SOTA TPI models at this point. But one thing we sort of show is that when the text prompt, when we gave like a lot more concept and attributes in the text prompt, for example, so like K here meaning the number of concepts that we use for generation. And if we use more than 3 or 4, most of the models have really bad performance. And even for the last performing model back then, was like DALL-E 3 still suffers when the performance, when the K is bigger than 5. And so yeah, this is the first takeaway. And then the second takeaway is that we trace back the performance limitation on the computational generation back to the training data. And we saw that the one potential reason why computational generation is limited is because the training data is not good enough. Of course, there is like awesome from modeling perspective explanation, as in people also talk about like Cliff model itself carries a lot of limitation in terms of like computational capability. But here we sort of study from the data perspective, and we look into the training data. So most of the models would still use the subset of line data set, and we tested out the subset on the line variant, and we show that across different concept categories, it doesn't have like a very uniform distribution. For example, the color and number has a lot of, and styles have a lot of representation, but for spatial understanding, it just doesn't really have a lot of samples. And that sort of limits, like we also showed that for different concept categories, the performance is different. So this sort of shows that why this is the case. And
Sorry,
another,
quick question.
oh yes,
How did you generate this plot? How did you determine if something has a shape or a size or number?
oh yes, so we look into the text prompt.
Okay, you look at the text prompt.
Right.
Is it like asking an LLM?
No, basically we use like 1,000 samples and then we identify, so we have a curative subset of the concept categories. So those are the concept categories, and then we look into whether they show up in the certain words show up in the text prompt.
And so if I understand correctly, is the idea here that if you were to change the text prompt, you would not see the issues you're identifying?
You're saying if we rephrase the,
Yeah.
yeah.
Okay, I see.
I
Okay,
think so.
okay.
Right. So this also shows, that's a great question, is sort of become the motivation for the next work I'm going to talk about. But yeah, so another thing is,
One other thing I had,
Oh,
the
yes.
T2I graph, you were showing with K increasing, the quality decreases.
Yeah.
How do you check that? Like, how do you measure that performance is decreasing? Is it very human based or
we use the GPT-4o,
to judge if it's correct?
judge.
Okay.
and I think the smart part is that we, so for example, we gave a text prompt, here we use like a cartoon style image shows a gray horse with a glass-like texture standing behind the tree. So like you can see there are so many different categories we care about here. And for each categories, we convert them to questions, but each question only evaluates one category. And then we gave, if we generate correctly, we give a green 1, otherwise 0. So in the end, if if any of them is wrong, so it score 0, otherwise 1.
Did you sort of calibrate, 'cause it seems like some of those things, for example, spatial relations, I feel like models are often particularly bad at because there's not usually much sort of grounding for that information. So I feel like, the question like, is the horse behind the tree? That seems like it would be both harder for the model to generate and also potentially less reliable for the model to evaluate. Like I think my guess would be that if you have a data quality, a lot of the similar data, or at least similar sort of data distribution, for the generative model and for the grading model. Did you look at whether like there are, there's basically sort of any sort of calibration or consistency challenges across the different types of, I guess, concepts that you would have to generate and then evaluate?
Great question. We actually we spent a really long time to do like a human evaluation stuff. So we say that GPT-4, like although GPT-4s we have like automatic evaluations, they have certain limitation, but it's pretty highly correlated with human evaluation result. And one thing about human evaluation is that like, human evaluators across themselves are also like not super consistent because there's so many concepts to evaluate, and and I would say it does do like I think even using the best grader right now as an automatic metric is like still have certain limitations, not 100% correct. But I believe that like later when we have a better sort of understanding model, it can be a better judge.
Cool. Well, I'm very glad to hear you ran the human experiments. That's great.
Oh yeah, my advisor asked us to run like the human evaluation. I think it was super helpful. So like obviously the design choice later, but yeah, we spent a really long time to do that.
Nice.
But yeah, and okay, so that's sort of the takeaway. Basically the takeaway is training data limited compositional performance. And we also said like most of the visual concepts that were included in the text prompt are under like most of the samples only include 2 to 3 concepts. So okay, that sort of the takeaway, like maybe 2 takeaways. One, current deep-learning model performance is like compositional performance is still limited, and second, the reason could be come from the training data. And then so we look into the training data at the end. So actually in this study we used the multimodal large language models, and I think the one that should be asked was super related to this. Basically, in this work, the only takeaway that you need to have from this work is that we sort of manipulated on the language space. And so we keep the image part frozen, but for the language part, we try to include much more complex question and samples, and that shows with only 10% of the samples can reach the 100% of the performance. So there are more basically are more juice to extract from the image part, and like you can do a lot more with richer text prompts. Yes. So okay, yeah, maybe just one sort of like yeah. So let's say this is a bunch of like motivation. I'm good at it. But yeah, so in short, even like vision instruction tuning data, current visual instruction tuning data, they are more focused on simple questions. And so like we showed that in our setting where we have more compositional tuning data, then the performance it's just like when we train on those data, it can more efficiently and effectively learn those capabilities.
Sorry, so K equals 1, 2, 3 is like some degree of compositionality.
Exactly.
Okay.
Yeah, like how many concepts you include in the question.
Oh, I see.
So, but yeah, I think that's
Can you show like the method, like how do you create that?
okay. Yes, so we sampled from the capabilities, and here we focus a lot on the visual capabilities, and basically we so the questions we want to make sure that the questions we generated can like basically cannot be answered without looking at the image. And I think it would be helpful to look at the prompt. So basically, this is the prompt that we use for question generation. So we gave them a case specific capabilities, and so the importance is if the question can be answered without looking at the image, it's a bad question. And it can be, this question should be challenging, but should have clear, unambiguous answers. Answers should be concise, and each question, must have a single question that naturally combines all given capabilities. So this is an interesting point because originally we don't include this prompt. Like usually the questions that generated are like 3 separate questions, but just put it in one sentence and separate it by comma. But that we also show that it's not really effective this way. So there are more other criteria we use to make sure that the generated questions are valid. So there are some more details, and I will defer that to.
Are you also filtering
That's
the
right.
generated questions?
Huh?
Are you also filtering the generated questions after this prompt?
Right, so we actually had this whole quality verification stage. So this part we check the capability usage, like does it cover all of the selected capabilities, and also the answer quality. Sometimes we use Gemini for this, and Gemini reply like, for example, NA or like no, or like those kind of questions will be related. And also we check their confidence score to make sure that the generated answers are not like super ambiguous.
So just to make sure I'm understanding, so the prompt is generated by randomly sampling from the counting and the spatial layout, etc. It's generated independent of the image, is that correct?
No, you have to look at the image in order to generate the question.
No, that's not the prompt.
Sorry, but maybe, so maybe, so I just make sure I understand. An image will be given, and then you will generate a prompt to elicit specific capabilities, correct? So like counting, etc. Is the prompt generated conditional on the image, or it's generated like independently, correct?
Oh, you mean, for example, in this case, the
Yes,
generated
for example, yes.
is conditional on the image.
So you're querying the LLM twice, once to generate the prompt and then once to get the answer, is that correct?
We basically generate the question, and then we did it together. So like the question and answer are generated together. That we asked it to generate them together. So like you only need to look at the image once. Do that.
I see.
I think Ricardo's question is how do you get the sampling of the capabilities that you want in the question?
So we basically so here's the step 1 is we select the capabilities.
Just randomly.
Randomly select.
Irrelevant of the image.
Irrelevant.
Okay, that was my question. I see. I see.
So before that, you need to have some set of concepts which actually repeat the image.
No, actually here, look at, so basically selected capabilities are like color. I want the Gemini to ask the question of this image on color and spatial relationship and object recognition.
Yeah, but I think Ricardo's point is that what if, for example, you ask it to do object recognition and there is no object in that image?
I'm really seeing ahead of me, but I think that was kind of work, but I think you're right because this is probably what step 3 is fixing. So like if you ask it like, hey, probably when Gemini is saying NA or I'm unable to answer this, it's probably because like you're asking it to generate the prompt and it's actually not relevant. Would be my guess that it's talking.
Right, great question. So we actually also filter out like do not create questions about object and features that do not exist in the image. Yeah, so, but if for example, if there's no certain capabilities in the image, those kind of questions will, for example, and if the answer A or no, those kind of question answer pairs will be related.
Yeah, exactly, no. And
Yes. So yeah, so for the experiment part, we showed that it has more than 100% performance compared with only like 10% of the data budget. So yes, some more details, but we also showed that if we scale the composition training data from 2K to 32K, like it continue to improve. And we also show that this training recipe, this data recipe has better performance on like even like more complex questions like resolve, like for example, a bigger than 3 case.
So I have one more question. Like, so because you're using the same image, like for instance, if you went from 65K to 6.5K, but generated 10 questions with like a random set of questions, like prompts, like have you ever done that kind of an experiment? Like how much juice can you get from the same image by asking it multiple sets of 3 questions?
Actually, yes, that's what we did. So people usually have like for the visual instruction tuning data set, people usually have one image with 5 to 10 questions. And so in our case, we generated basically we make sure that k equals 1, k equals 2, k equals 3 each have 2 to 3 randomly like 2 to 3 question answer pairs. So we make sure that each image are associated with like 6 to 9 like question answers. Yeah.
did you see, so you saw like great improvements overall, and if I'm understanding correctly, like your synthetic data generation strategy is for like k equals 2 plus compositionality stuff, right? Did you see any regressions on like k equals 0 evaluation?
Oh, great question. K equals 0, we actually look into those questions. I actually gave a bunch of samples in the appendix or in paper. Basically those k equals 0 questions are like translate this from, for example, English to Korean. So like it's not like the K, because we define K as vision centric capabilities and which is not our focus. So I think for those knowledge based or like very language centered tasks, that's like I would assume this approach wouldn't help too much. Yes.
When you're training with multiple like question answers for an image, like do you put them all in like as one training sample, or is it better to like have different samples of that? Because you can imagine that like if you have multiple question answers in the same like training sample, it pays attention to the other question as well, which is maybe not the desired behavior.
So the models are yes. So basically, let's say each image associated with 6 to 9 question answers, right? They're treated as 6 to 9 different samples.
Different samples.
Yeah.
Okay.
They're not under one sample.
I see.
Yeah, and in that we did a bunch of like understanding stuff, but yeah, I think I don't want to let people be hungry and not have much, but yeah, I think that will be it. I think looking forward, there are so many interesting questions down there. Let's wrap, and I'm excited to have this guest afterwards.